Okay, we are ready to resume. In 1988, carbon-14 findings from 3 AMS labs independently dated a sample removed from the Turin Shroud, unarguably the most widely studied linen cloth in history. The dates reported ranged from AD 1260 to 1390, thus leading to the conclusion that the cloth originated in the Middle Ages. Since the dating, many hypotheses have been proffered attempting to explain the C14 results, which appear contradictory to a plethora of data pointing to a more ancient origin. An acceptable hypothesis of why the shroud dated between 1260 and 1390 must satisfactorily explain the precise, statistically determined angular skewing of the dates corresponding with the individual laboratories, with reference to the location of the subsamples received. The hypotheses of generalized ionizing radiation, thermal effects, environmental carbon monoxide enrichment, deliberate tampering or substitution of the samples, and bioplastic coating are incapable of meeting this latter requirement, as is the premise that the cloth itself is in toto medieval. In 2005, Ray Rogers authored a paper in Thermochemica Acta that reported the results of experimental tests evaluating the hypothesis that the radiocarbon dating of the Turin Shroud was invalid due to the intrusion of newer material in the sampling area. Based on data obtained from his analyses of samples from the area, Rogers concluded that the combined evidence from chemical kinetics, analytical chemistry, cotton content, and pyrolysis MS proved that the material from the radiocarbon area of the shroud is significantly different from that of the main cloth. Rogers identified an organic dye made from madder root, calcium, and gum arabic, along with an aluminum mordant. What we plan to present to you in this portion is additional documentation from a previously unpublished 1978 STIRP study that clearly delineates surface chemical differences between the radiocarbon sampling area and other parts of the shroud, excluding the charred areas. In addition, new data will be examined in light of existing radiographic findings, textile evidence from the adjacent Ross sample, blinded expert analysis of the C14 subsample from Zurich, one of the labs to date the shroud, and independent microscopic confirmation of surface contaminants in the Holland backing cloth C14 region, and historical restoration information documenting known techniques resulting in both front and backside invisible repairs. One of the numerous scientific tests conducted in '78 by STIRP included spectrally resolved quad mosaic photography. This study, utilizing state-of-the-art NASA technology of the time, was designed to generate color discriminability products capable of conducting a chemical distribution analysis of the surface of the linen cloth. According to the STIRP researchers in charge of this study, quote, "The generation of color products was considered the most important image processing task. From a color-enhanced relative color display, the color of different features of the image can be compared," end quote. In other words, different colors indicate different chemistries. The technique employed principal component analysis, also known as Korhuna-Love transform. Researchers at the University of Kent explained that, quotation, "Multispectral imaging entails acquiring several images of the same scene using different spectral bands. For instance, a digital color camera detects 3 separate images for the red, green, and blue components of light," end quote. The STIRP authors noted that, quote, "If the chemicals were spectrally differentiated, the multispectral classification process could provide a map of chemical composition throughout the shroud image," end quote. In keeping with this objective, our paper includes a critical evaluation and related discussion of the previously unpublished original 4 quad mosaic images to identify areas of chemical correspondence pertinent to the radiocarbon sampling area. Evaluation of the image from the ventral lower corner depicts the radiocarbon sample area next to the Holland cloth, which is observable due to the missing 5.5 inch by 3.5 inch corner piece. According to textile historian Mechtilde Fleury-Lemberg, who observed the area during her work to restore the shroud in 2002, both of the shroud's missing corner pieces were already missing prior to the addition of that backing cloth in 1534, which had been added during repairs made damages in 1532. Both the exposed Holland cloth and the adjacent radiocarbon sample area are a uniform dark green color. The ventral corner section consists of a unique, uniform, solid dark green region in a rectangular pattern with distinct borders. The dark green encompasses the side seam and extends approximately an inch into the main shroud cloth region. Similar solid geometric patterns with defined borders in this hue are not observable elsewhere on the cloth. Also observable in this quad mosaic image are several areas showing charred cloth that resulted from the 1532 fire. These areas and other charred areas throughout the cloth range from medium to a very dark green. Non-charred areas also contain some scattered dark green color in random patterns and with indistinct borders. Images of the larger dorsal missing corner piece section, also exposing some of the Holland cloth, have a completely different chemical color signature consisting of a myriad of lighter tone colors. Noteworthy is the fact that the color variation within the dorsal section Holland cloth does not extend into the adjoining side seam or main cloth section, as it does on the ventral side. In terms of evaluating the reliability and validity of the quad mosaic to reveal true surface chemical discrepancies via the color patterns on the shroud versus reflecting simple illumination variations, evidence for this can be found in the images of the known patches attached to the shroud. The clear differences among the patches with differing historical provenance and thus different preparation techniques supports the assertion that the quad mosaic images provide valid indicators of surface exposed chemical variation throughout the shroud. Research has demonstrated that the charring of cellulose materials significantly increases carbon content, about 20 to 30%, as compared to corresponding non-charred material. The carbon content of charred cellulose and cotton ranges from approximately 43 to 71% of total weight. As such, it is possible that the quad mosaic's chemical color signature, reflecting the medium to a very dark green on the charred portions of the linen shroud, may represent carbon. Rogers observed copious amounts of gum arabic on yarns obtained from the radiocarbon sample area. Gum arabic is composed of pentose sugar units. Rogers further identified the organic dye made from madder root along with calcium. Although unconfirmed, the calcium may have been calcite. Calcium carbonate was used in medieval dyeing and may have been incorporated with the red madder, which was typically used with a white base. Each of these substances, identified by Rogers from the radiocarbon sampling area, is composed primarily of carbon. The quad mosaic reflects significant differences between the two exposed ventral and dorsal Holland cloth sections in the excised corner regions. The dark green signature is missing from the Holland cloth on the dorsal region of the cloth. Conversely, the exposed ventral region Holland cloth, side seam, and adjacent radiocarbon sampling area consist of a deliberate, uniform, and well-delineated dark green chemical signature. The spectral discrepancies noted between the two exposed regions of the Holland cloth is likely explained by the observation that these are two separate pieces of cloth added to the shroud at different times and under different circumstances. First recognition that the Holland cloth was not a single uniform piece of material came following radiographic examinations by the Sturp team in 1978. Modern, London, and Morris found that, quote, the Holland cloth is not one piece, but instead 3 pieces hand-sewn together, end quote. Fleury-Lemberg further noted that, quotation, the lining had been made wider by the addition in the length of a 30-centimeter wide strip in order to match the width of the shroud. This added strip consists of 2 pieces, end quote. Fleury-Lemberg also found the 2 pieces were stitched together, forming a transverse seam. The smaller of the 2 pieces from the added strip was under the ventral missing corner C14 region. Also in the ventral missing corner section, which we hypothesized to consist of a restorative surface dyes and what was unlikely an undocumented invisible medieval repair, is the section from which the 1973 Ross sample was extracted for analysis. In this sample, Ross found that the side seam had been attached to the adjacent main shroud by a 2-ply linen sewing thread. By removing the sewing thread, Ross was able to separate his sample into 2 distinct pieces, which he identified as piece 1 and piece 2. Each piece exhibits different characteristics, such as cotton content, lignin content at the growth nodes, and thread size, suggesting 2 different origins of the yarns. Further, the significance of the sewing thread Ross identified is that its character and quality along the length of the side seam were observable via radiographic examination. Sturp researchers reported that, quotation, the radiographic images substantiate the 4 to 5 millimeter width of the seam. In addition, 2 rows of stitches, one along each edge of the seam, are observable, end quote. Fleury-Lemberg makes an important observation about the side seam and adjacent stitches, quotation, the sewing has been done from the reverse of the fabric, and the stitches have been executed with great care and are barely noticeable on the face of the shroud, end quote. While topside radiographs of the ventral corner show a continuous sewing thread next to the side seam in the C14 region, beyond this region, the stitching becomes intermittent and barely visible in the main shroud, as confirmed by Fleury-Lemberg. The continuous, fully observable sewing thread represents a significant change of technique and suggests this section of thread, which incorporated the Ross sample and C14 sample areas, was applied from the top instead of the reverse of the cloth. This further implies the 2 sections of sewing threads, C14 versus main shroud, were applied at different times and by different artisans, with the main shroud stitching possibly coming from the same time period as a cloth from Masada in Israel, dated to BC 40 to AD 73. Another distinctive characteristic of the cloth also points to a pre-medieval origin of the shroud. Although debated in the past, image analyses tools and techniques have clearly identified the existence of horizontal and vertical bands throughout the shroud. According to the Cambridge textile book, quote, tapestry-woven coverlets and hangings were characterized in Hellenistic and early Roman times by shaded bands, which incorporated subtle colors of graded yarns. Combined later with figured designs, shaded bands had vanished by the 4th century, end quote. Thus, the shroud with its shaded bands could not likely have been created after the 4th century. As we first described in a paper in Orvieto, Italy in 2000, Other observations support the assertion that expert and undocumented manipulation took place in the C14 sample region. Independent blinded analyses by textile experts of the Zurich subsample used for C14 dating also revealed significant discrepancies in the two sides of the sample. In the analysis of the subsample, Albany International Research Company Louise Harner remarked that, quote, "The float is different on either side of the sample. It forms a thick, thin pattern on the right side, whereas the left is much more consistent throughout," end quote. Harner surmised that this was due to each side of the pattern being woven independently. As mentioned previously, Rogers reported finding significant amounts of surface contaminants on both the RAS and C14 yarns. In contrast, he reported that, quote, "There was absolutely no coating with these characteristics on either the Holland cloth or the main part of the shroud," end quote. However, independent microscopic analysis of one of the yarns extracted from the ventral corner exposed Holland cloth by microscopist Joseph Kolbeck of Hercules Aerospace revealed copious amounts of unidentified red particle contaminants. This discrepancy may be explained by the different locations from where the Holland cloth samples were taken. Reports indicate that while most of the Holland yarns were extracted through burn holes in the main part of the shroud, one yarn sample, which Kolbeck examined, was taken from the exposed Holland cloth in the ventral corner. According to Kolbeck, his sample from the ventral corner was not returned to Rogers for comparative analysis, thus confirming the above scenario explaining the different results. This supports the quad Mosaic findings showing that the same surface chemistry extended from the ventral exposed Holland cloth into the adjacent C14 region material, but varied considerably from other regions of the Holland cloth and main shroud. An archaeologist, the late Dr. Eugenia Notowski, who obtained numerous shroud fibers from Rogers, conjectured that the red particle contaminants discovered by Kolbeck were the burial spices aloe and myrrh. However, this assumption was based solely on her comparison of the debris with reference photos of the suspected substances and not via chemical analyses. She reported, quote, "The study could go no further beyond photo comparison because of the inability to perform testing which would either remove or destroy materials from the tapes," end quote. Along with the lack of any chemical characterization of the debris, the fact that the singular yarn, designated 1FH, with the impurities came from the ventral missing corner exposed medieval Holland cloth and not the main shroud, argues strongly against Notowski's assumption that the debris was from burial spices. Based on the quad Mosaic data and Rogers' findings, it is far more plausible that the 1FH impurities were also red matter and gum arabic as chemically verified by Rogers in multiple adjacent samples. The quad Mosaic images, radiographic findings, textile evidence from the adjacent RAS sample, blinded expert analysis of the Zurich C14 subsample, and independent microscopic confirmation of surface contaminants in the Holland cloth C14 region support Rogers' assertion that a surface dye was added to the shroud in the area of the 1988 radiocarbon sampling to disguise an undocumented repair. These data further confirm that this substance included the exposed Holland cloth on the ventral, but not dorsal, side of the cloth. Thus, the application of this substance occurred sometime after the Holland backing cloth was attached to the shroud in 1534 and prior to the 1973 RAS sample extraction, but was intentionally added to only one side of the cloth. These data further support the theory that the radiocarbon sampling area was manipulated during or after the 16th century. The RAS sample is highly significant due to its thorough examination and adjacent location to the C14 sample area. Given the stark differences between yarns found in the Raz pieces 1 and 2, combined with the existence of the sewing thread, which connected the two disparate materials, we hypothesized that piece 2 was the original shroud material seam, and piece 1 was a cotton-containing patch made to resemble the original shroud cloth. In this paper, we have also discussed additional supporting evidence that not only is the Raz and C14 sampling region anomalous in comparison to the main shroud cloth, but the piece of Holland cloth in the ventral corner is also significantly different from the rest of the Holland cloth. The most probable scenario is that the original smaller section of Holland cloth was extracted for relics. This section was most likely replaced with newer material that did not match the exposed dorsal section of Holland cloth. Also consistent with the data is the hypothesis that the person or persons responsible for taking this section of Holland cloth also extracted a small section of main shroud cloth directly adjacent to the side seam and missing ventral corner, i.e. the C14 sampling area. To hide the extraction, the missing material would have been patched and surface dyed, along with the newer backing material, such that it would not have been detected. Starch, which was identified in this area, was routinely used by medieval restorers to disguise invisible mending. Historical evidence demonstrates that it was not only possible for medieval weavers and embroiderers to invisibly mend textiles such that they were not topside detectable, but it is also recognized that they could choose whether or not to permit their handiwork from being detected on the backside as well. Quote, historically, reweaving was not carried out through a support fabric and was often executed so skillfully that it is not always recognizable as a later addition, although differences in the rate of dye fading have often revealed its presence. Evidence of reweaving would now, meaning 16th century, usually be left deliberately visible on the reverse of the tapestry by the presence of warp ends and knots, end quote. As this passage infers, skillful medieval weavers could choose whether or not to leave evidence of their work on the backside of a fabric. Although less than conventional restoration practice, it is known that in the early part of the 16th century, the art of reversing was practiced such that tapestries could be viewed intact from either side of the cloth. Quote, in August 1524, Wolsey's wardrobe of the beds were shorn and new dressed on the wrong side, end quote. Reversing resulted in the lack of any telltale signs of a backside repair. It has been previously hypothesized that if an undetected 16th century repair impacted the C14 sampling area, the ratio of medieval to first century material would have been approximately 60% to 40% based on expert observations. However, the area would have been a mixture of both age groups. In this scenario, it is important to note that there is a requisite overlap and intermixing between the newer patch material and the existing textile via the integration and splicing of frayed edges into the damaged textile and vice versa. The unavoidable interweaving required of this invisible mending technique would, most assuredly, have created heterogeneity in the C14 sample area. It is worthwhile to go into some detail explaining what splicing is and how it pertains to the Shroud's carbon dating. Splicing is a technique of joining two yarn ends by intermingling the constituent fibers so that the joint is not significantly different in appearance and mechanical properties with respect to the parent yarn. The effectiveness of splicing is primarily dependent on the tensile strength and physical appearance. The splice is comprised of three distinct regions elements, defined by wrapping, twisting, and tucking intermingling. We had hypothesized, and Rogers later confirmed, the existence of a spliced yarn among the Ras samples he had received. According to Rogers, Ras number 1 was straight as received, indicating it was likely a warp sample. The splice was identified by Rogers as being 1.4 millimeters long. It would be hard to detect this feature in the weave, but notice that one end of the yarn is colored and compact, while the other is fluffy and whiter. The colored end shows the gum coating on its surface, which is not on the inside. This color-enhanced rendering of the Ras number 1 thread shows the comparative areas of overlap, twisting, and intermingling as described in the above illustration. Further discussion on the chemical and physical nature of this yarn and its surface contaminant will be provided in a separate paper in this conference after ours. The exact ratio of patch versus original threads is not determinable by photographic analysis alone. However, a well-supported estimate based upon weave pattern changes has been posited, reflecting approximately 60% of the C14 sample consisting of 16th century threads, while approximately 40% were 1st century in origin. The radiocarbon date was calculated using the percentage of observed 16th century versus 1st century weave types appearing in the Oxford subsamples. Representative dates were 1500 for the 16th century and 75, AD 75 for the 1st century. As proposed in our hypothesis, a sample containing approximately 67% of AD 1500 radiocarbon and approximately 33% of AD 75 radiocarbon should yield a calibrated date of about 1210 AD, which is what the Oxford obtained in their C14 dating. In terms of the C14 area in relationship to the water stain, which has been posited to be much older than the 1532 fire and also impacted the sample area, photoanalysis demonstrates that this latter assertion is incorrect. This photograph, when placed next to an image showing the location of the reserve versus C14 sample, clearly demonstrates that the entire C14 sample area was outside the water stain region. The crease can be used as a marker to compare the two photographs and location of the C14 sample. Further, it is also notable that the reserve sample does not appear to have any water stain markings. According to the illustration of the water stain area, the stain should have gone directly through the midsection of the reserve sample, forming a distinct marking discoloration. Since the sample does not show any evidence of a water stain marking, this could very well be explained by the later addition of a patch in this area. Given these new data, we have amended our previously proposed historical scenario describing what happened in the C14 area. We believe that it is still possible that Cardinal Louis de Gouravad, overseer of the Shroud in the 1530s, cut out the 5.5 inch by 3.5 inch corner adjacent to the C14 area to use for relics. This could have been done prior to the addition of the Holland cloth and would not have included the side strip seam. Note the frayed edges in the slide. At some time after the Holland cloth was attached to the shroud and after the shroud left Chambéry, expert embroiderers took a section of the Holland cloth from under the missing corner and stealthily took a main shroud souvenir, in quotes, next to the cutout. The embroiderers left the original side seam intact in order to make it easier to reattach the new patch material without being detected. The embroiderers replaced both the Holland cloth relic and small shroud snippet with a cotton linen blended fabric, surface dyed the cloths to match the much older main shroud, and stitched the patch back to the original side strip seam from the top of the cloth. We contend that the most likely time period by which this undocumented activity occurred, in our speculation of course, was between 1535 and 1541, when increased exposure to the populace and lower security during this tumultuous time period may have provided the opportunity for an unauthorized relic taking of the shroud by an expert embroiderer. Rex told the story of Uncle Gilbert giving away shroud samples. Relic taking and relic giving has always been popular. It was back then and it still is now. In conclusion, it is impossible to quantify the amount of surface carbon, other contaminants, or intruded newer material into the radiocarbon sampling area based upon the quad mosaic or other data presented in this paper. Similarly, it is impossible to determine if either the surface carbon or the manipulation it represents had any impact on the 1988 radiocarbon dating. However, in light of these new data, along with a recently posited theory that does not preclude a first century origin for the cloth, additional radiocarbon dating incorporating other areas of the cloth is recommended. Further, characterization of the remaining C14 samples, raw samples, and the Holland cloth to ascertain the presence of cotton, surface dyes, and other restoration substances in accordance with these findings is warranted.